This is our last video in classical mechanics, and hopefully you've been able to see the pattern here. We've started with talking about dynamics of non-deformable bodies, so rigid bodies, and then statics of non-deformable bodies, statics of deformable bodies, and now dynamics of deformable bodies. So you can see the pattern in how we've separated out these various topics within the context of classical mechanics. So this last topic is dynamics of deformable bodies. Normally goes by the terms vibrations, mechanical vibrations. And we're going to focus specifically on the wave equation. So we're going to derive the wave equation in the context of the lateral vibration of a string. So you can think of a stringed instrument such as a guitar. We pluck the guitar string and the string vibrates up and down. So we want to determine that vibration displacement amplitude V of xt. This is very similar to a problem that we looked at very early on in our discussion of Hamilton's principle. There was the static deflection of a string with a lateral load f of x across the length of the string. Here we're going to take away that lateral load, but now we're going to add the possibility of this moving. So it's a dynamics problem rather than a statics problem. We still have the tension P and its length 0 to L in our domain x, and then the vibrations will occur in x and t. So the displacement v of xt then is our dependent variable. This is obviously a continuous system now because it's a deformable body, so we'll have to use the continuous form of Hamilton's principle. The rho here is the mass per unit length of the string, just like it was in that earlier case. And we're going to assume that this transverse deflection is small. We discussed this in that earlier statics example. I won't go through all that discussion again. You'll see how that assumption simplifies the equations. But again, refer back to that earlier example to see some of the more detailed discussion on that issue. So let's look at the kinetic and the potential energy now per unit length. Remember, in these continuous problems, the T's and the V's and the L's, in fact, are per unit length, per unit area, or per unit volume, depending on whether it's 1, 2, or 3-dimensional. So in this case, it's 1-dimensional, so it's per unit length. So it's a script T. The kinetic energy is 1/2 times the mass times the velocity squared. Now the mass is going to be mass per unit length. So that's the rho. That's the mass per unit length of the string. And then the velocity, V, is the displacement. So the time rate of change of that displacement will be the velocity. So partial V, partial T. And then, of course, that's squared, velocity squared. So 1/2 rho times the square of partial V, partial T. The potential energy, in this case, again, per unit length, so script V, is just the strain energy of the string. So once again, we talked about this in the previous statics example. In that case, we had two contributions. We had the fact that the string could stretch like a spring, and also the fact that there was a force acting through a distance. Now we don't have that lateral force acting through a distance, so we just have the strain energy due to the stretching of the string because of the P and the vibration. So that is the script V is then du dx, where u is the strain energy. We're talking about a little differential piece of the string, so it just has a small strain energy du, and divide by dx, the length of that little differential piece, to get the strain energy or potential energy per unit length. Now I'll go through this next bit somewhat quickly because we did the same analysis before for the statics case, and it's no different here. So we have, just like a spring, the restoring force, which is minus P here, times the elongation. So that is the strain energy in a little differential piece of the string, and it's the negative of that. So we have negative, negative, positive, and P times the elongation. Elongation of each little differential element is ds, which is current arc length of the little differential element, minus its original length, which is dx. So ds minus dx. ds, that's arc length. So as usual, that's the square root of 1 plus u prime squared. Okay, now our dependent variable is v, and it has two independent variables, so we have to use a partial derivative. So instead of v prime, it's v sub x, or partial v, partial x. So in any case, it's the square root of 1 plus the square of partial v, partial x, times dx. So you factor out the dx, and you have this expression here. Then, if you remember from the statics case, to get from here to here, we took advantage of this assumption of the small displacement. We used the binomial theorem expansion to get an approximation for this square root, and that resulted in this. So it can be approximated as 1/2 times P times the square of partial V, partial x, times dx. Again, exactly the same as for the statics case. So we combine the kinetic energy and the potential energy per unit length to form the Lagrangian density, or Lagrangian per unit length, for the vibrating string. The total Lagrangian then is you take the Lagrangian density, the script L, and you integrate it across the length. So you take the Lagrangian per unit length and integrate it along the length, and that gives you the total Lagrangian, capital L. So that's 1/2 times rho times the square of partial v partial t, the kinetic energy, and minus 1/2 times p times the square of partial v partial x, which is the strain energy. Then we have Hamilton's variational principle, where you take the variation of the integral over time now. So you notice we have an integral over x, spatial coordinate, and we have an integral over time. So 2 independent variables, 2 integrals. So the variation of the integral over time of our Lagrangian, which is the Lagrangian density right here, as you see. And so we have 1/2 then times the variation of the time integral, the spatial x integral of the thing in square brackets here. So this is Hamilton's variational form for the vibrating string problem. And we'll talk in a moment about what this says physically about what's happening with the vibrating string. But before we do that, we can get the Euler-Lagrange equation, the differential form of this variational Hamilton's principle. And that turns out to be the wave equation. I haven't gone through the details here. I haven't taken the variation and done the integration by parts, but I'll leave that to you. And you get the wave equation, partial squared v partial t squared. Again, v of xt is the displacement of this vibrating string, is equal to gamma squared. Gamma squared is capital P over rho, and that's the wave speed of a wave traveling in the string. Depends on the tension. So that's why in a stringed instrument like a guitar you can change the tension, because that'll change the wave speed, divided by rho. And again, if you look at a stringed instrument, that's why you see different masses per unit length of each of the strings, times partial squared v partial x squared. So this is the wave equation. Now one thing you'll notice, and we'll talk about this in the next slide, is this actually looks very similar to the Laplace equation. The physics is completely different. The solutions are wildly different, but the equations look very similar. And we'll discuss how that actually makes sense from the variational point of view, even though the equivalent differential version, the Euler equation, doesn't necessarily make that so clear. This is again supporting one of the themes that I've been emphasizing, is that the variational form oftentimes provides additional insight and intuition into the physics of a particular problem. So let's discuss that a little bit more. So here's what Laplace's equation would look like. Partial squared v, I'll use the same dependent variable, partial x squared plus partial squared v partial y squared is equal to 0. So if you just bring this over to the left-hand side, you have partial squared v partial t squared minus gamma squared times partial squared v partial x squared. Now you notice a few differences. Some of them aren't terribly important. So here we had the 2 independent variables x and y. Here we have x and t. Doesn't change the mathematics. Here we have a gamma squared. Here there's no coefficient. Again, doesn't change the physics of the underlying problem. But the one thing that is fundamentally different is here I have a plus sign, so it's the sum of these 2 terms, whereas here when I bring this over, I have a minus sign between them. And that's reflected in the variational form. Here I have a minus sign, whereas the variational form of Laplace's equation, which we saw back in chapter 2, has a plus sign here. And this is the point I want to make. The presence or absence of that plus or minus sign makes all the difference in the world in terms of the physical behavior that's being manifest by these equations and therefore the corresponding systems. So this first point is the one that I just made. Essentially, the only fundamental mathematical difference between these 2 partial differential equations is one has a minus sign, one does not. And so the question is, how does that minus sign, or lack thereof, lead to qualitatively different behavior, fundamentally different physical behavior? That's what we want to discuss. Thinking back to Laplace's equation, remember Laplace's equation governs diffusive processes. These are smoothing processes. So whatever the initial distribution of something is, Laplace's equation wants to smooth it as much as possible. And we saw that in the variational form of Laplace's equation. We saw that it was the sum of the magnitudes of the gradients in the x and y direction that were being minimized. So it wants to make those gradients as small as possible in an integrated sense across the entire domain. The difference here is now in our functional, again, because we have this minus sign, we still have the squares of these two gradients, but it's the difference between those two magnitudes rather than the sum of the two magnitudes. And what I want to show you that while the consequences of that difference are not apparent in the differential form, they are more apparent in the variational form. So again, it's the difference between the magnitudes of the gradients that's now being minimized in the context of the wave equation. So what difference does that make? So if I were to put in a spatial distribution, so if I were to pluck my guitar string, put it in a spatial distribution, I introduce a disturbance into the system at t is equal to 0. Now the question is, what does this equation, what does the variational form of the wave equation tell us will happen to that disturbance as time evolves? Well, what we see that is rather than smoothing out the disturbance because of the sum of the magnitudes of the gradients being minimized, instead the system is going to generate a temporal disturbance, so a disturbance in time, in the form of a traveling wave. Now this gamma squared, that's the wave speed. That determines the speed at which the wave moves along our string. So once we introduce that spatial disturbance at t is equal to 0, the equation takes that and produces a traveling wave. Now because of this difference of the squares, it's the magnitudes of the gradients that have to match in order to minimize our functional. So what that means is we're going to get both a positive and a negative traveling wave that are produced. So I put in the disturbance, and I'm going to get waves that are moving to the right and to the left, both at the same speed and both with the same energy. They're identical, but one is moving to the right and one is moving to the left. So essentially half of the energy that I put in the initial disturbance going in the right moving traveling wave, and the other half is going in the left moving traveling wave. So they'll look identical, but moving in different directions. And again, that's because it's the difference of the squares. So because of the square, you get a positive as well as a negative. What I hope is that as you think about and reflect on, for example, the variational form of Laplace's equation, wave equation, what I hope you can see is by looking at these variational forms, you can learn more, you can gain more intuition about the underlying physical processes, whereas the differential Euler form often hides that to some extent.